Hello, I am Alberto Solera. This is my third year in the PhD program under the supervision of Stefano Dicetti and Carlos San Miguel, and I'm working on active flow control using data-driven algorithms. I work in Tattoo. Well, we know that about 5% of Europe greenhouse gas emissions come from drag losses in transport. We know that active flow control can be applied to reduce that losses in more compact, more flexible, constrained conditions than traditional approaches. And we want to apply data-driven algorithms to tackle that problem, as it is an ongoing field of research. All in all, we want to move from traditional geometry optimization for drag reduction to more compact approaches. This is an example using synthetic jets in a track. It still has some geometrical modifications. This is from 10 years ago. We want to remove ideally the geometrical modifications. We are dealing with turbulence in active flow control. Here we have the traditional problem of a multitude of temporal and spatial scales. However, we also know that there are some coherent structures that sometimes, in some problems, can be modeled by low-dimensional attractors. And our objective is to use that, to leverage that low-dimensional attractors and coherent structures to build effective control algorithms or systems for this kind of nonlinear systems. We already published it, and I presented it last year, a paper in Nature Communications where we use a beta variation autoencoder to compress a flow field from a chaotic wake in only 10 to 20 size latent space. There's a huge reduction here. We show that these low-dimensional attractors in fact exist. Using the autoencoder, we can compress more effectively the information than using linear methods, such as PhD. And we also show in this paper that the model can generalize to unseen data during training. And this is something that was new in bibliography. There were sometimes some tricks to some cheating, maybe. From this system, it was a non-control system. We moved to a control system. Here we are encoding snapshots of the fluid pinball problem, and with PhD or autoencoder. And we want to predict the latent space using autoregressive models that use also the control signal, the control input, to propagate into the future the latent space. So it's more directed towards the model of control system. Here we use LSTMs to predict only the next time step, multi-step prediction, or also a more complex approach using the LSTM and a numerical integrator. And here, thanks to Patricia for his amazing work. And using this approach, here we have some results. On top, there is the ground truth. We can see on the left the compressed snapshots by PhD and autoencoder. We can see that the PhD produces lower frequency, spatial frequency results. There is some smoothing there. And it makes the temporal modes easier to predict. So the prediction sometimes works better for PhD. But of course, the autoencoder is able to better reproduce the field. However, it's sometimes harder to predict. So there is sometimes a balance. In this case, the prediction works better for the autoencoder, of course. But this is not always obvious. Then we move to build controllers from offline data without direct interaction with the real system. First, we build an open loop activated dataset. Here we can see the atomic example where the control input are those jets at the bottom. And this is sometimes not so straightforward for this kind of oscillating or unstable system with delay, because the wake affects the near field. So we will a control signal that tries to excite the frequencies around the expected sensitive frequency, that is the wake seeding frequency. Here we use a frequency and amplitude modulated sine wave to excite and explore all the dynamics, as much of the dynamics. Using that dataset, we build a model where we use surface pressure sensors in the body and force measurements. And using that data-driven dynamics model, we produce the controller. Using offline training, we can make it easier because we don't have to implement the training online. When we apply the controller to the system, it is already trained, so it produces a deterministic output. It will be stable and safe. And it also has learned from a richer data set because we have explored more of the dynamics of the system using this smart control input signal. To build the controller, we have explored two architectures. This is the first, most simple model, where we use a past series of control and sensors with an LSTM predictor to predict the forces and the next time step, and also sensors, so we can apply it recursively. And then, as the challenging point here is to generalize, we build a more complex model where we use an intermediate latent space and separate model to encode, predict, and map from that latent space to aerodynamic forces. We can apply it to recursively. We also test this model using two approaches, the model predictive control and reinforcement learning, as I already mentioned this morning. With model predictive control, we can manage constraints on control inputs more easily. And also, maybe more important, we can change the cost function at any time, not before the problem starts, but during time. For example, if our model produces some uncertainty measurement, we can avoid using that unreliable model regions. Reinforcement learning, on the other hand, is fast. We only need to forward pass the controller neural network, and we have the control signal. We tackle that in model predictive control using gradient-based GPU optimization. We use the same framework used to train the neural network to optimize the control signal, and it's quite efficient, but not as fast as reinforcement learning. Reinforcement learning, on the other hand, is prone to exploit the model uncertainties to find weak points, and also the cost function is fixed once the model is trained. There are some results of the approach. As we can see, both approaches reduce the drag about 10%. In the model predictive control works slightly better here. They are not able to fully stabilize the wake because it will be too much of an extrapolation from the training results. So it is able to reduce the drag, but not to extrapolate so much. And the planning for this year is to continue work on these reduced order models, to apply it for control frameworks, hopefully to publish the remaining work, maybe a couple of papers. One of them is in the making, and hopefully to present and defend the thesis. So far, the main achievements have been that Nature Communications paper, a conference presented by Carlos in Turin past September, and we have a couple of works accepted in two conferences in Malaga and Dublin this summer. And that's all. Thank you for your attention. And